Okay, in this lecture we're going to look, so we're looking at Cartesian products, ordered pairs. We've got ordered triples, but we can keep going. We can talk about ordered, what are called tuples, right? So this is kind of the thing where if you want to talk about bit strings in terms of sets or passwords in terms of sets, you're going to want to talk about ordered tuples. So an ordered tuple, an n tuple has its so the tuple means that it has n elements and they're ordered. So first, second, third, etc. Round brackets to signify that they're ordered. And where did they come from? Well, this comes from one set, the second thing comes from a second set, etc. So this could be read as the, yeah, well, it is what it is there. Let's see some examples. So we'll also use we saw the notation or squared for the Cartesian product of or and or cubed for the Cartesian product of 3 copies of or. So similar story, we'll keep on going, a to the n to be the Cartesian product of n copies of a. So for example, let's take an alphabet a that's made up of 10 digits, 26 small letters and 26 big letters. Let's just write down the number of things in this alphabet is 62. 10, well, 26 makes 52, plus 10 makes 62. Passwords of length 4 with characters from the alphabet A are described by elements of a to the 4, which is a times a times a times a. And they are what are called, I suppose they'd be ordered quadruples. And so if for example, I wanted to use the password JP85, it would be given as this ordered tuple, JP85. The order is important, so I use the round brackets. And everything, J, big P, 8 and 5 are all elements of. So the J is an element there, P is an element there, 8 is an element there, and the 5 elements there. And the number of passwords, you can just keep doing the Cartesian product thing, and the number of passwords of length 4 here will be each element of a of this Cartesian product is a password. So the number of elements in here is the same as the number of passwords, is the number of elements in a Cartesian product, a Cartesian product, a Cartesian product, a, and you can show that this is a times, when I say a, number of elements in a, times number of elements in a. In other words, the number of elements in a to the power of 4. And in chapter 26, chapter 4 will answer questions such as, given an alphabet of a given size, what should be the minimum length of password? What should be the minimum length of password to ensure that there are, say, 1 million different passwords? Okay, so we're going to tuples, the appropriate language to describe passwords of a given length. Okay. Similarly, binary or bit strings also fall under this framework. Take length 3 binary strings. Viewing, say, 010 as 010 and ordered triple, we have that the length 3, the set of length 3 binary strings is the Cartesian product of 010101 equal to 01 cubed. So we can actually write this down. So this would be, say, the first one. And remember, we did this thing before where we counted from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. So now it's probably harder to make sure if you gotta yeah, but here it is anyway. Okay, so this is all the possible triples, the first thing being in 0, 1, the second thing being in 0, 1, and the third thing is in 0, 1. And we've seen before that subsets of A can be paired with length A binary strings, and that means that there's a set isomorphism between Binary, this is isomorphism, sorry, that's a word we don't know, but basically it's kind of just saying they're kind of the same thing. Subsets of A is the same as, we've done this already, length A binary strings. So this is another way to find the cardinality of the power set. The number of subsets of A is the same as the number of binary strings of length cardinality of A, and this we can show using a similar, so this is okay, so this is number of things, so you got Cartesian product of 0, 1 with itself A times, where A is the number of elements in the set, and using the thing above here, this would be number of elements in 0, 1, which is 2 by 2 by 2 by 2 A times, which is 2 to the power of the number of elements in A.